Good morning. Let's begin today's program. So this is the first section with two speakers. So the first speaker is Antonio Castro Neto. Professor Guang-Yu asked me to introduce a little bit about him, but I don't prepare. But I say something. So actually, just from my memory, and Professor Castro Neto graduated from University of Illinois at Champaign, and worked with vacuum, right? And then he moved to UCSB as a postdoc. Then he moved to UC Riverside, and actually I am his first graduate student. So after that he moved to Boston University and go to Singapore University as a director of 2D Materials Center. Right? So let's welcome Professor Castro Neto. And his talk today is 2D materials, science and technology. Let's welcome Professor Castro Neto.
I want to thank the organizers for inviting me to come back to Taiwan. It's always a great pleasure to come here. If you look at the title and the abstract I wrote, I realize it's too ambitious, although it's just one line, my abstract. I tried to change, I realized that this audience would be more interested in theoretical aspects of 2D materials. And I decided to change a little bit the content because I think it would be more appropriate for this audience. Okay, so the Center for Advanced 2D Materials exists since 2010. Initially it was called Graphene Research Center. We changed our name in 2014. And in there we have around 50 professors in the center. And we have facilities to do experiments and synthesis and characterization and devices, everything under the sun for 2D materials. And we also have a theory group. And I want to talk about some of the work that is being done there on theory of 2D materials. So this is a slide that I've been using since more or less 2005. I have been involved with graphene from pretty much the very beginning. And the people working in this field, especially André Geim and Castro, who were awarded a Nobel Prize in 2010, it was very clear that graphene was just the beginning of a journey. Okay, so it was the first material that was isolated in monolayer form, but it was very, very clear that it was one of hundreds, maybe thousands of different materials available for scientists to study. So this is actually this paper that was published in 2005 at the Proceedings of the National Academy of Science in the United States, to me, is the most important paper they ever wrote. It's even more important from a scientific perspective than the paper that gave them the Nobel Prize, which was a paper about graphene in 2004. Because what they showed in this paper is that essentially many different layer materials can be isolated in monolayer form. Okay? And for instance, this is, of course, from graphite, they isolated graphene, but also, for instance, for molybdenum diselenide, which the semiconductor, they also isolated. This is niobium diselenide, sorry, which is a charge dense to a superconductor. The isolated monolayers, molybdenum disulfide, which is a semiconductor, and even high temperature superconductors, then they can be isolated to monolayer form using this mechanical cleaving with a scotch tape. So this is really important because it opened up the doors for the exploration of materials beyond graphene. Actually, compared to graphene, graphene is pretty boring from the electronic perspective, okay? It's a non-interacting system. It's described by a very simple equation, and everything that was predicted theoretically for graphene actually was confirmed experimentally. I don't recall a single theoretical prediction that was not confirmed. Why? Material is too simple. Okay? So there is no complexity in graphene. So it's very easy. So for us it was a great playground, but it's not so challenging from the theoretical perspective. These other materials are way more challenging. They are more complex. Okay? They have much deeper physics behind. Okay? And this is, I want to talk a little bit about that. And this has to do with the electron-electron interactions. Okay? So electron-electron interactions in graphene are very weak. The only thing they do is to change the speed of propagation of the electrons, nothing else. But in these other materials, electron-electron interactions actually produce phase transitions. They produce new states, correlated states. And this is why they are more interesting from the physics perspective. And of course, much more challenging for the theorists. Okay? So, there is so as I said, there is the nice thing about all these materials is that the electrons, they have to move from atom to atom by going through orbitals. Okay? Many years ago, there was a big field of research called two-dimensional electron gas. What's essential is that you confine the electrons to an interface, and the electrons move there pretty much freely, like plane waves. Okay? In these materials that we're talking about here, it's completely different. The orbital physics actually plays a very important role. And we know from experience in strongly correlated electron systems that orbital physics is actually fundamental for new phenomena. Okay, because as you confine the electrons in an orbital, they are forced to interact with each other. And when they interact, then you can get magnetism, you can get superconductivity, you can get new states of matter. Okay? So, in fact, many people working in this field believe that the key to understand, for instance, high temperature superconductivity or heavy fermion behavior or something like that, they actually see these planes, okay, of these layered materials. I'm going to get back to that later. Anyway, but also the nice thing about these materials that first they are so thin, they have atomic thickness, so they are all transparent. So essentially, they are perfect for optics. Doing optic application. Actually, optics of 2D materials is a huge field now. Okay. The other thing is that they are soft. You can bend them. You can make creases. You can fold them. You can do lots of things with a structure that you cannot do with a traditional three-dimensional material. You cannot just take a piece of gold and bend. Okay. You can if you apply a lot of strain, but it may break the crystal. These materials you can fold very easily. Okay? Their bending stiffness is very small when they are in monolayer. You can apply strain, and with the strain, actually, even for applications, strain is very important. In the electronics industry, they use strain to change characteristics of transistors and things like that. And these materials can also be strained, and they change their behavior under strain. And for the chemists, actually, this whole area became very fruitful because these materials can be functionalized. Essentially, you are doing surface physics with these materials. And we had a huge experience on surface physics. But now you have a material which is a pure surface. It has no bulk. Essentially, it's a surface, it's two sides with no bulk. And this, for chemists, this was a good playground. And now chemistry of 2D materials is a big field right now. Anyway, but there are many of these, probably around thousands of these materials that we know. In the center that I direct in Singapore, we probably have explored hundreds. And this is really like the very beginning. It's the tip of the iceberg. We don't even know how many of these materials exist. We have no idea. Okay? So it's a huge place for exploration in material science. This won't work. Okay. So there is also one material that I like very much, and you see why I like this material very much. It's called black phosphorus. Okay, black phosphorus has this kind of structure here. It's a layered material where the atoms make this structure that goes up and down. It's pure phosphorus. So in this sense, it's very similar to graphene. Okay, it's just one atom in the structure. And why I like this? Because the more atoms you have in the unit cell, the bigger is the probability of getting disorder. Okay? So if you have a huge unit cell, like for instance, this is not so big, but like this, or this, you can have replacement of atoms, you can have atoms changing position, and that introduces disorder. In a pure monoatomic material, that doesn't happen. You can have vacancies, maybe, but you don't have extrinsic atoms in the crystal structure. So you guarantee, in some sense, that the order, the crystalline order, is better preserved. Okay? And this is the case. This material can be exfoliated down to monolayer form, like all this, and it's a semiconductor. So it has a lot of interest in the electronics industry. Two-dimensional semiconductors may play a big role, for instance, in flexible electronics, which is an area that many industries are very interested. Okay. So this is actually, black phosphorus is one element of that appears in a class of materials called transition metal monochalcogenides. Okay, I'm sure that, I'm not sure, but I guess many of you heard about transition metal dichalcogenides. But these are monochalcogenides, and these are examples. For instance, you have this structure like black phosphorus, and the difference is that you have usually a chalcogen, like sulfur, selenium, and so on, and a metal, in this case tin or germanium, and so on. And they make this structure, and these materials, they can be synthesized, and they can be exfoliated down to monolayer form. All these materials, they have very interesting property, like, gallium arsenide, that is used in semiconductor industry. They are all semiconductors. Okay? And these are semiconductors with different gap sizes that go from the infrared to the ultraviolet. Okay, so this gives you an opportunity to explore semiconductors with different gaps, with different gap sizes. And of course, we know this from technology, that being able to have different electronic gaps gives you opportunity of different applications. From digital electronics to optoelectronics, for instance. So this is why these materials are so interesting. Okay? And of course, you can calculate, so for instance here, this one in the gap, it turns out that it changes with the number of layers. So if you put more layers or less layers, you can also control the size of the gap. So the band structure can be engineered in many different ways. Okay, either by choosing the material or by stacking the material in the right way. Okay, so in fact, it's well known for people who work in this field that the biggest challenge in dealing with these materials is not synthesizing them or anything like that, is actually manipulating them. Because you have a film that is just one atom or two atoms thin. So how do you manipulate this mechanically to actually, for instance, layer these crystals on top of each other? Okay? Now there are companies that are selling machines that do that. Okay, so we created actually a new business, which is to have these machines that can actually make a sandwich with films which are just one atom thin, which is extraordinary. Okay? So anyway, so this is just an example. So as I said, this material, black phosphorus, the monolayer form is called phosphorine. Okay? It has very high mobility. It's a direct band gap semiconductor, and it's very anisotropic. This structure, as you can see, is very anisotropic. The crystal structure is very anisotropic. And this has very interesting consequences, for instance, for optics. Okay? So you have dichroism, you have many different things that come from the fact of the low symmetry of the crystal. And this can also be used, for instance, in applications. All right? So, and you can fold, you can do all sorts of things. So, for instance, the gap is always at the center of the Brillouin zone, which is also very interesting for people doing optics, because you do direct transitions in the center of the Brillouin zone. And the gap changes with the number of layers, as I said before. Of course, life is not perfect. So here, no, but before talking about that, this is bulk. So the gap's around a fraction of a volt, and it goes to a volt when you go to the monolayer form, as I was telling you before. So, but the issue here is that, like surfaces, so anyone here who ever worked with surfaces, they know that the first thing that happens when you get a fresh surface is that they oxidize. Right? So any metal exposed to air will have an oxidized surface. Right? Not only metals oxidize, semiconductors also oxidize. Now graphene has an advantage in regards to all these materials we're talking about, because carbon is a very small atom. And so the distance between carbon atoms in the graphene structure is very small. So it's the areas for oxidation are higher. In fact, we should be very grateful to that, because we're made out mostly of carbon. Otherwise, we would die much sooner by oxidation. In fact, we die by oxidation, if you think about it. Okay? We eventually oxidize and die. And these materials are the same thing. They oxidize and die. Okay, so oxygen makes us alive, but also kills us in the end. Okay? And here is no different. But the nice thing about these materials is that we can find ways to reduce or eliminate oxidation, okay, in a way that they become very useful for applications. Okay, so this is an example of studies of what happens if you have oxygen in the crystal structure of phosphorine at different positions. So this is another thing, because the crystal has low symmetry. The oxygen can enter in many different positions, you know, in the structure. It can make bridges, like an epoxy type binding, or it can be just like connected to an atom. And what happens is that this has a direct consequence in the band structure, obviously, because once the oxygen is there, in a semiconductor, you're going to generate what's called mid-gap states, which are impurity states that exist either in the center of the gap or close to the band edges. So the type of defect that you find in the electronic structure depends very much on the position of the oxygen in the crystal structure. Okay, so a lot of time is spent understanding oxygen in these materials, but this should be no surprise for people working, for instance, in traditional semiconductor industry. Okay, semiconductor industry spend a lot of time, a lot of money to understand defects in silicon, in gallium arsenide. Okay, so there is nothing surprising about this. You need to, because you want to have a super crystalline material with very large electron mean free paths, with very high mobility, so your devices operating the way you want them to operate. This is no different here. The difference here is that when you're talking about silicon, you're thinking of impurities inside the bulk. Here we're talking about surface defects. Okay? But that's exactly the very similar. So, but the interesting thing is that actually this is a numerical study of the possible oxidized forms of phosphorus. It turns out that you can have crystal oxides of phosphorus. Okay? And in that case, these crystal structures actually, they are periodic, they are crystalline, and they have different forms. They can be like tubes, or they can have this structure here. And the interesting thing is that if, and this has not been done experimentally, this is very challenging. If you can oxidize phosphorine in a controllable way, you can extend the gap from, say, 2 volts up to 8 volts. So you can go all the way to almost to the X-ray. Okay? So oxygen is not necessarily bad all the time, it's just that you need to understand how to control the oxygen. And it's not an easy molecule to control because, or atom to control, because it's very reactive. Oxygen wants to donate electrons, right? This is, you know this from basic chemistry, right? So oxygen always wants to donate electrons to close its electronic shell. So the problem is just how to control. This is still a challenge, but you know, maybe it's something we should explore more. So how did we manage to control? I told you, graphene doesn't oxidize. So the solution is essentially you just cover the surface of phosphorine with graphene. This is called encapsulation. Actually, we don't use graphene most of the time, only when we want to make electrical contact. What we use is a different material called boron nitride, which is a wide bandgap semiconductor, 5 electron volt gap, and also very stable in air. Okay? And then what we do, essentially, we lay down boron nitride on top of the phosphorine. Okay? It covers completely it. It's inert. It doesn't change anything on the electrical properties and make the system extremely clean. And it doesn't oxidize anymore. So actually this was proven experimentally in our labs. Another thing that it's very interesting is that sometimes we find defects in this material that we didn't expect before. For instance, in this case, this is actually data. This is STM data from Lu Jiang's group at NUS on some defects that are found in phosphorine. Okay? And this is actually the numerical simulation, so which we believe that this is coming from either vacancies or tin. Sometimes you can have these atoms there. Depending on how you produce the black phosphorus crystal, you may have some of these atoms there. So again, it goes back to semiconductor industry, understanding different types of defects that can be created. The nice thing is that you can really probe them using, for instance, STM. It's very easy to probe these things. This is, sometimes we want to do things intentionally. So in this case, we did an experimental study of copper. You put copper on top of black phosphorus and you look at what happens. So these are band structure calculations of copper atoms on phosphorine. And what we find is very interesting. Of course, copper is a metal. When you put on top of a semiconductor, it dopes. It donates electrons to the semiconductor. But in this case, not only that, it affects the size of the gap. Okay? Actually, this experimental data, okay, without copper and with copper, and you can see this is the IDV, so you can see the current versus voltage, and you can see a shift of this the IDV and a shrink of the band gap in the system, actually in agreement with band structure calculations. Okay? So it's very good that we can explain these things with actually very simple calculations like that. But it's not always the case. So this is with potassium, again, alkali metal. So you dope these materials with potassium, and again, it donates electrons, and you change the size of the gap. And again, these are experiments, so these things you can do in the lab, and you can test the predictions of the theory, and everything works out very well, okay, for this type of material, phosphorine. An interesting thing about these monochalcogenides is that just like in the case of gallium arsenide, for instance, you have spin-orbit coupling. And spin-orbit coupling is very interesting, of course, for many things, including spintronics. Okay? And this is an example, for instance, of tin selenide. The interesting thing is that you see, tin selenide is an indirect band gap semiconductor. And what you see is that the spin-orbit coupling actually affects very strongly the conduction band. So people who work in traditional 3D semiconductors, you know that usually the effect of spin-orbit coupling is in the valence band. Okay? In these materials, actually the effect is in the conduction band. Okay, so that's one of the characteristics of the band structure of this material. So this has very interesting consequences. I'm going to talk more about this in a little while. So another thing, because of the very low symmetry, this material doesn't have inversion symmetry, these crystals show piezoelectricity. Okay? So if you compress these materials, if you apply uniaxial pressure, you actually get electric charge out of them. Okay, which is something very, very interesting for many different types of applications, because you have a piezoelectric material which is just essentially one atom thin. Okay? And actually the elastic moduli is very high. In fact, these materials, I already talked about this. Because of time, I'm going to shift. Now just one comment about this. As I said, oxygen is fundamental. Understanding what oxygen does here is very important. So what we found out experimentally is that black phosphorus is more unstable than, say, these monochalcogenides in regards to oxidation. Okay? And why is that? It comes from the fact that actually in these monochalcogenides you have two atoms, two different types of atoms, and it's harder for the oxygen to actually bind to the structure because they have even lower symmetry than black phosphorus. Okay? And in fact, these oxygen defects, when you compare the energy for oxidation, actually the energy for oxidation in, say, something like germanium sulfide, okay, are much higher. So in fact, these materials are very stable in air. Okay, if you take black phosphorus, you leave half an hour in air, it's gone. Okay, but these materials, they can remain in air for a long time. Okay, and we can explain that using band structure calculations, by looking again at defects. So again, defects in semiconductors is something to understand. It's very important, so you can explain things that are hard to understand without doing these calculations. Let me move on. So this is all non-interacting physics. Okay, it's essentially, I'm telling you that band structure calculations, which are essentially non-interacting calculations, can describe very well these things, defects and things like that. Now let's move one notch up in terms of interactions, which is excitons. Okay, excitons are very, very important in semiconductors because they are responsible for the optical response. Okay? So, and there are different types of excitons. One of them is the Vanier excitons, which is very delocalized, and we have Frankel excitons, which are very localized, and that depends essentially on the Coulomb interaction between electrons and holes in the semiconductors, right? So it depends on how the electrons and holes interact. So this is an example of excitonic calculations. This is for germanium selenide. And one thing that we realize is that in these materials, if you really want to do a good calculation of exciton binding energies, you have to go beyond traditional numerical approaches. You have to do more complicated calculations like what's called GW. It's a self-consistent calculation that puts in the calculation the electron-electron interaction at a higher level. Okay? So, for instance, this is a traditional DFT, results of band gap. The difference, for instance, if you do DFT for germanium sulfide or selenide, the gap, say, is a 1.7 eV, but GW brings it much closer to the real gap, which is 2.85. This happens because in two-dimensional systems, electron-electron interactions are much stronger than in three-dimensional systems. Why is that? Electromagnetism happens in three-dimensional space. The electrons here are moving in two-dimensional space. Okay? So the electric field lines, they actually propagate away from the plane of motion of the electrons. If there is no dielectric medium outside of those layers, there is no screening. So essentially the electric field can propagate freely, okay, in the empty space. And that part of the electron-electron interaction is not screened. If you have a three-dimensional metal, the electric field has to propagate through the entire metal. And so the electrons in the 3D material will have a strong impact on how the states interaction is screened. So this lack of screening leads to an enhancement of the electron-electron interactions. So two-dimensional materials are naturally more strongly correlated than three-dimensional ones. And of course, one-dimensional materials are even more, right? So, and what I'm saying is that even for things like band gaps and excitonic states in these materials, you have to take into account this. If you want to understand electron-electron interactions, you really have to take them into account from the very beginning. And so this is an example of the absorption spectrum of different materials. And you can see here this light gray is actually just DFT. And you see what happens when you do, so say, something like GW. The shift in spectral weights are very large. Okay? So if you want to understand the optical absorption of these materials, you really have to do something better than traditional band structure calculations. Okay? And in fact, these calculations, if you do GW, which by the way, for people who do computational physics, they know that GW is from computer time. It's enormous amount of time, compared to any DFT, but it's essential, it's fundamental if you're trying to understand things like optical absorption, okay, because of this enhancement of the electron-electron interactions. So this is an example of these calculations. This is for, say, germanium sulfide. This is how an exciton looks like. It's more like a Frankel exciton. You go for germanium selenide, so you change the chalcogen, and you go to a Vanier exciton. Okay, so a simple difference of substitution of selenium and sulfur actually changes completely the binding energy and changes the nature of the exciton state. Okay, not only that, as I told you, we never do experiments with these materials in empty space. Nobody goes in the space shuttle, exfoliate graphene in the vacuum and do that. We need substrates. So the dielectric, as I said before, the dielectric environment becomes extremely important. Okay, this is an example, for instance, of the excitonic energies for these two materials, germanium selenide and sulfide, as a function of the dielectric medium, okay, that you put. So the substrate where you put these materials on top. And this is what happens when you have in vacuum. But if you have a silicon oxide substrate, the binding energies change tremendously. Again, because of the way the electric field is modified by the presence of the dielectric medium. So, interesting thing, now you can control the exciton energy by selecting the substrate. If you do mica, you get one thing. If you do silicon oxide, you get something else. If you put one boronitride, you get something else. So there is this now possibility of controlling the excitonic states from the outside by just changing the substrate where you actually deposit the material. How much time do I have? 10 minutes. So, as I said, spin-orbit coupling plays a very important role here, okay, in these materials. And as I said, usually you have to, in most of these materials, you have transitional metal atoms. So essentially the electrons propagate through either d or p orbitals, okay? And spin-orbit coupling essentially has two pieces to it. So this one couples the orbital motion to the electron spin, and this one is a spin flipping term. So essentially, if the orbital angular quantum number changes, the spin quantum number has to change as well to compensate. Okay? And the other part of the spin-orbit coupling, which is this LZ, which is the Z component of the angular momentum and the Z component of the spin, essentially they shift, essentially split the energy states depending on the relative orientation of the spin. So these are the two major components in a spin-orbit coupling. Now, when you have these materials, what happens is they are not in the same plane. One atom is in the lower plane and the other atom is in the upper plane. So these orbitals are not aligned. Electrons, when they move from orbital to orbital, they go through non-orthogonal orbitals in the system. Okay? This does not happen in 3D materials. This is very particular of lower dimensionality. And the fact that this structure is not flat. And what this allows is something very interesting that you don't see very often, is that an electron with spin up can move to the atom on the same layer with spin down. Okay? So it looks like, if you look at just the one layer of atoms, it looks like that you have a spin flip in the hopping process. Okay, and this comes about in these materials because of this asymmetry that they have. Okay, so this is coming from the this part. So essentially, in these buckled lattices, it allows coupling between opposite spin components, okay, in the same orbital. It doesn't happen in traditional 3D systems. And the consequences of that is very interesting. So this is an example. We created numerically an artificial lattice, or 2D lattice, okay, with essentially where you have one atom here, usually can be a heavy. If you want very strong spin-orbit coupling, you choose a very heavy atom, right? Because remember, spin-orbit coupling grows with the 4th power of the atomic number. So basic atomic physics, right? So if you take a material, an atom like lead, which is heavy, or bismuth, which is heavy, then spin-orbit coupling becomes very large. So you can explore this physics in a bigger way. But essentially it's like this. So this is a square lattice, and you have this up and down thing. And the interesting thing, you look at the band structure, all these materials, they become semiconductors. They are semiconductors. But the interesting thing about these materials is that they have this level crossing here, which actually comes about purely from the spin-orbit coupling. It's the result of this spin flip process I was talking about. Okay? And actually these are different. You can make a mono, of course, numerically I can make whatever I want, but like tin, lead, bismuth, and this is the band structure that you get. And all of those have these crossings here, which essentially can be written as, described as a kind of Dirac Hamiltonian, okay? Which is actually has a Rashba form. So you get a Rashba Hamiltonian in a system without having an electric field. Because Rashba usually requires the presence of an electric field to break symmetry. But this comes about here because of the band structure, and it doesn't break any symmetry, actually. Okay, and actually the properties of these crossing points is very, very interesting. It's very different from graphene, and you know, it's a topic on its own. Okay, so this is an example of, this is a stable structure that we believe can be done. So this is copper. One can grow lead on copper 100 surface, and the stable structure will be this one I was talking about. But this again is a theoretical proposal. It has not yet been achieved experimentally. This area of strong spin orbit coupling in 2D materials is really just starting. I believe that there will be a lot of things coming about. Since I don't have, I was going to talk about superconductivity, but since I don't have time, I'm just going to conclude here. Okay? So what I was trying to tell you here is that this field, it's really in its infancy. Okay? There are things that we don't know very well. We're just playing with them and trying to understand. And from the science perspective, as more and more materials become available experimentally, this field is going to be driven by experimental physics. Okay? Not by theoretical physics. But more and more materials becomes available, there's going to be more and more phenomena to study. Okay? And another thing that I think it's the consequence of all this is that this is going to have a big impact in the industry. It's going to generate new technologies because you're talking about materials which are very different from ordinary materials we are used to, especially on the semiconductor side. So my perspective is that this is going to be a big area in the near future as we synthesize better crystals, as we make them more pure, more crystalline, and so on. The path that we are taking is no different from what happens in the 1950s in the traditional semiconductor industry. Remember that in 1950, semiconductors were not traditional. Okay? People had TVs with valves. I still remember, you know, when you have these big Russian valves in the TVs. Okay? So at that time, it was exotic. Now it's trivial. All of you have computers, iPods, iPads, whatever, you know. But at that time, this was exotic physics. Now what we have here is a similar story. So give it a decade, and you see that this is going to grow very fast and is going to be present in everyday life. In my opinion, there is no question of that. With that, I want to conclude. Thank you for your attention and the invitation to come. Thank you very much.
Thanks for a nice talk. And I want to say something. Actually, I met Antonio several years ago, and he told me he had two choices to go to UCLA or Singapore, but he chose to go to Singapore. And since
much more money there.
And he told me last night he even set up a lab to do experiment. Okay, let's open question. Open for question.
I have one, by the way, thanks for the nice talk. And you indicated that the field will be driven by experimentalists. I say experimentalists. I love that. However, I think in this field, a lot of time, it is also let's see. It is because experiment takes a long time. So as a result, a lot of work are also inspired by theoretical calculation. So don't.
By the way, I'm a theorist.
I know. I am an experimentalist, and then you advocate for experimental. Now I want to advocate for theorists. I'm interested in this. What you talk about? This is a lab on copper 100. So one of the things about material is, does the material stable? Are they thermodynamic stable? Can we make them? Is there any evidence that this single layer lab can work on copper 100?
Yeah, this is the result of numerical simulation. According to the numerical simulations, this is stable.
Oh, does it show superconductivity?
I hope so.
Okay.
Thank you. A very nice talk. As you mentioned that oxidation is quite important, and because silicon is a kind of a God-given material because it naturally oxidizes to give a very nice insulator layer. So I wonder that in the phosphorus case, did you consider that how oxygen can go far through the inside from the surface? Do you know how the oxygen can go through it?
No, this is actually a very good idea. So we thought of that. So maybe if we can do controlled, you don't need to work with a monolayer. You know, if you work with a few layers, it's enough to get a lot of interesting physics. One of the things that we thought is whether we can control the oxidation in such a way that we can oxidize just the first layer, and that protects everything underneath. The problem is that there are so many pathways for chemical reaction, you know, so the control has to be extreme to the point that essentially what you have to do is that you have to oxidize the material inside of a glove box with minimum amounts of oxygen, and this is very hard, and you know, but it is something that we want to explore, whether we can do the passivation of the surface without having to put boron nitride on top. But now the nice thing is that, you know, we already have these technologies. We can do this very fast. We just take this into the clean room in a glove box, and you exfoliate in the glove box, and you deposit boron nitride. It's like minutes to do. So, you know, the question is that for basic science, there is no point. But for industrial application, I think this has to be done. Because, you know, to transfer this boron nitride in an industrial setting is not something easy to do, exactly because of mechanical limitations.
two questions. One is this group 4 monochalcogenides you mentioned. That's you show that the acetone can change quite a lot going from sulfide to selenide. Is that because the orbitals are more extended?
Yes, exactly.
Now my question is that experimentally you see very strong acetone in molybdenum disulfide. I guess that because it's a direct band.
Yeah. There are many differences here. Right?
What happened to gallium monoselenide because it's indirect band? Do we still see strong acetone
Yes.
in optics?
In all these monochalcogenides, you see very strong excitonic response.
But that's theory, isn't it? I wonder whether it's dark acetone or visible acetone.
Right. But let me tell you something which is very different between dichalcogenides and monochalcogenides. Symmetry. The dichalcogenides have much higher symmetry than the monochalcogenides. Okay? So the optical response is not only stronger because of the density of states effects and things like that. It's because the material is so anisotropic. You can select the response that you want by just changing the polarization of light. So this is a very useful tool for optical studies, you know. And another thing that we see, and this is why the lifetime of these excitons is much longer, because they are much cleaner. The monochalcogenides are much cleaner than the dichalcogenides because of what I told you in the very beginning, that it's much easier to desorb a dichalcogenide than a monochalcogenide because of the fact that you have more atoms in the unit cell. The binding is much stronger. And so to get this extrinsic impurities and so on is much harder. And then that means that the lifetime, so it's not just the strength of the excitonic resonance, but also how narrow this resonance is. It's important here. So lifetime effects are much, much more interesting in monochalcogenides.
Another simple question is this black forest, phosphorus you mentioned.
Yeah.
You seem to say that there's a circular dichroism.
Yeah.
But I don't see how this can come from in a simple physical picture.
Yeah, you have to look at the band structure.
Uh-huh.
Okay, so maybe if I can get that band structure, if we can find it. Yes. So you probably cannot see very well on this slide, but you see here in the valence band, it's actually very flat. There are two valleys.
Oh.
Okay, so all these materials, they have two valleys in the conduction and valence band. So essentially now there is an interesting thing. So you have what people call valleitronics, because using polarization of light, you can choose what valley you excite. And if you have spin orbit coupling, you have spintronics together with valleitronics. So the number of combinations essentially increase a lot. More quantum numbers, more interesting physics.
Thank you.
Last question.
Okay, I think I would like to go back to the metallic layers, lead on copper, because both of them are FCC metals.
Yes.
And the lead is constant, copper is 3.6, lead is 4.9, it's pretty big.
Mm-hmm.
So, but I saw your structure that you're stretching the first layer lead to be twice of the copper lattice constant in the second layer. So when you say it's stable, have you ever compared the energies of just lead bulk, whether this layer were wet or not? It would just become a single, cluster.
Without the copper.
No, the lead.
The lead.
The two layers.
It's not. It's only when the bilayer form it becomes stable.
Compare with the energy of
Compare
lead clusters.
Yes.
Okay, let's thanks.
Thank you so much.
Okay.